Hey everyone, Happy New Year! I'm your host CP, and welcome to the third episode of Help I'm Teaching, a podcast for amateur educators. This podcast is meant for people who aren't professional teachers, but love to teach. Maybe you have a young cousin who's really into bees, and you want to discuss it with them, but you don't remember studying pollination since high school. I'll provide you with an outline of the topic, dispel some common myths, create some helpful analogies, and leave you with relevant questions to discuss. Maybe they'll grow up to be a world-saving entomologist, or maybe you will. Or maybe you'll both leave the conversation a bit more curious about how the world works. Either is fine. I'm a graduate of Cornell University in plant science with a minor in biomedical science, and I'll be generally covering related topics, but could always branch out if needed. Today I want to talk about acids, bases, and pH. It seems scary, and you can definitely lose the interest of your students if you get too excited, but the underlying concept is simple. pH is all about hydrogen. Why is it spelled like that, and what does it mean? pH stands for power of hydrogen, specifically hydrogen ions. pH is the negative log of the concentration of hydrogen ions. We do the negative log instead of just the unaltered concentration of hydrogen, because the concentration can vary immensely to a magnitude of 10 with 12 zeros behind it, and it would be really difficult to deal with. The negative log allows for a simple change of plus or minus 1 to represent the concentration being multiplied or divided by 10. Whether a substance is basic or acidic depends on the concentration of hydrogen ions, H plus, to hydroxide ions, or OH minus. More hydrogen ions mean a lower pH and more acidity, and more hydroxide means a higher pH and more alkalinity. You could use pOH to measure how basic a substance is, but it's a lot simpler to stick to the standard methods. pH is usually measured on a range of 0 to 14. There are a few different definitions of acid and base floating around there. The traditional one is known as the Bronsted-Lowry definition of an acid and involves hydrogen and hydroxide as we just discussed. Acids donate protons or hydrogen ions and bases accept them. This is probably as far as middle school goes. Some more complex definitions like the Lewis definition involves substances that have neither hydrogen or hydroxide like aluminum chloride or AlCl3. Aluminum chloride acts as an acid by donating electrons to other compounds. But don't worry too much about these if you're just introducing the concept of pH. These come much later. Now I want to talk about some equipment you might be using, so you can be a bit more familiar with how they work. Bromothymol blue, or BTB, is a common reagent in pH demonstrations, and it is green initially but changes color when the pH changes. As the pH becomes more acidic, it turns yellow, and if it becomes more basic, it turns blue. One thing you can do with this is a CO2 demonstration. Adding CO2 to water creates carbonic acid, so you can add BTB to water making it green, and when you blow bubbles into the water with a straw, it'll turn yellow. This can also help explain how climate change creates acid rain and ocean acidification. Just make sure you or your students don't drink it. pH strips are another tool used to get a general idea of pH. These are strips that you immerse in a substance and change color depending on a substance's pH. You compare these colors to a chart that usually comes with the box to determine pH. However, both of these methods rely a lot on how you evaluate the colors and aren't reliable. For a scientific measure, researchers use pH probes, which are electronic instruments that work by measuring voltage. A solution of pH 7 is inside the probe tip, and when electricity is run through it, it produces a certain voltage based on the amount of hydrogen ions present. This voltage is then compared to the voltage of the sample you're measuring. Probes measure this voltage difference and interpret it as a pH. Generally, when acids and bases react, both are neutralized and you get water and the salt. Think of the chemical reaction NaOH plus HCl, or sodium hydroxide, as base, reacting with hydrochloric acid. The sodium with a positive charge and chlorine with a negative charge will create sodium chloride, or common table salt. If you notice what's left over, you see 2 hydrogens and 1 oxygen. Sound familiar? Yep, H2O, or water. You might be demonstrating the reaction between an acid and a base using the classic example of vinegar, an acid, and baking soda, a base. When they're combined, the mixture will fizz for a time before stopping. This fizz comes from the production of CO2 from carbon and oxygen atoms, but this doesn't happen with all reactions. NaOH has no available carbon or oxygen to form CO2, and indeed if you watch this reaction on YouTube, the only thing that happens is the pH indicator changes color with no fizz. Now, as always, here's some common misconceptions. Not all acids are bad for you. Cartoons may have your students thinking that anything acidic is bright green, bubbling, and corrosive, but acids are very common in food. If you're into cooking shows, you'll often hear acidity thrown around when people cook with ingredients like tomatoes and coffee. Acidity provides a unique bitter taste that can balance flavors and can be used to tenderize meat. Acidic foods are also harder for microorganisms to grow in, extending their shelf lives. Bases like baking soda are used in baking, reacting with acidic ingredients to produce carbon dioxide. This is the reaction that causes dough to rise. So there's plenty of relevance outside the classroom already. You might have heard of people drinking alkaline water or telling you to avoid acidic foods. Is there any truth in this? Yes and no. Alkaline water is said to help deacidify your blood and prevent osteoporosis and aging. However, blood acts as a buffer, or to put it another way, blood has an ability to resist drastic changes in pH. Buffering is very important in the blood. In what's known as the Swan and Pitts experiment, a dog's blood was infused with 14 millimoles of hydrochloric acid. This caused a pH change of 7.44 to 7.14 in the dog's blood, or a hydrogen ion rise of about 36 nanomoles per liter. To put this in perspective, if nanomoles were people, it would be like if the entire population of Tokyo tried to get through a single door and only 36 people got past. You really don't want the pH of your blood to change because certain proteins in the blood have a very narrow tolerable range. All kinds of proteins, like enzymes for reactions and proteins that carry nutrients around your body, have an ideal pH. Outside of this pH, the amino acids that make them up will be missing a proton or having one they don't need, making them useless for their role. For example, in cells, the pH of mitochondria is consistently kept at 7.2 to 8.2, fairly basic, while lysosomes for digesting cellular debris are around 4 to 5 pH, much more acidic. If the pH of the mitochondria dropped to 4 or 5, a lot of key enzymes would be degraded and wouldn't generate energy very efficiently. Blood pH is actually a diagnostic in some diseases like diabetes, kidney disease, and drug overdose. In the case of diabetes, lack of insulin can cause acidic ketones to be released into your blood, lowering the pH and causing a dangerous condition called ketoacidosis. So if your blood's pH was that sensitive to what you eat and drink, you'd probably get some serious conditions very fast. Okay, what about acidic stomachs? Some people are more prone to high stomach acid, but it can also be caused by bacterial infection. High stomach acid has a variety of unpleasant symptoms like stomach aches, nausea, and vomiting. When you have an acidic stomach, your stomach acid is not dilute enough and the lining of your stomach is being digested. During acid reflux, this stomach acid travels up your stomach to your esophagus, causing even more discomfort. Tums, an over-the-counter treatment for acidity, is composed mainly of calcium carbonate and works by increasing the pH of your stomach. You might hear the terms strong and weak referring to acids and bases. The terms strong and weak acid or base aren't totally in line with how dangerous it is, and instead has to do with the ions it's composed of. Something classified as a weak acid can still hurt you at a high concentration. Hydrofluoric acid is a weak acid, but penetrates the skin quickly and is extremely dangerous to inhale. Hydrochloric acid in your stomach is a strong acid, but vomit doesn't immediately burn surfaces. This quality is known as corrosivity for acids and causticity for bases. While they are correlated with an acid being weak or strong to an extent, what will be more relevant at this level is the concentration, or how much water is mixed with the acid in question. An acid being strong or weak has to do with how readily it dissolves in water, and not how dangerous it is. Now here are some questions you or your students might have. Is water an acid, base, or neutral? Pure water is neutral, meaning a pH of 7, but tap water can range from 7 to 7.5 due to minerals and impurities. Water has a special property of acting as an acid or base depending on the reaction. It can both give up a hydrogen ion and become hydroxide or OH- if exposed to a base, or it can accept one and become hydronium ion, which has a formula H3O+ if exposed to an acid. This is known as an amphoteric substance. Just like how frogs are amphibians that can survive on both water and land, water can act as both an acid and a base. What are the pH ranges that are dangerous to us? Anything below a pH of 2 or above a pH of 11.5 is dangerous to the skin. The pH scale goes past 0 and 14, but these compounds aren't generally seen outside of labs, and that's a good thing. If you want to show a dramatic demonstration of the effects of pH extremes, look up piranha solution on YouTube. It's an extremely acidic mixture of sulfuric acid and hydrogen peroxide. Piranha solution is usually used for cleaning organic materials off of lab equipment and is called piranha solution because it looks almost like a school of cartoon piranha chomped on whatever it reacts with. Is there a difference between alkaline and basic? Basic refers to compounds that reduce the hydrogen ion concentration of a substance, for example by increasing the hydroxide concentration. Alkaline means basic compounds that are soluble in water. All alkalis are basic, but not all bases are alkaline. Examples of bases that are not alkaline are some metal hydroxides like zinc hydroxide. Using base will probably be correct more of the time since it's more general, especially if you're not sure, but it's good to be aware of the distinction. What are some ways we can tell if something is acidic or basic without things like pH strips or indicators? One way is taste. Everyone knows how the acidity of lemon juice and vinegar create a sour flavor that makes you scrunch your face. Meanwhile, bases tend to taste bitter instead. Just remember two things. Any method that relies on subjective measures like taste don't have scientific rigor, since they can be informed by our own experiences and personality. And of course, don't taste acids or bases unless you know they're safe to consume. You can also try introducing an acid or a base and seeing if a reaction occurs. For example, if you wanted to know if something was acidic, you could add some baking soda and see if a reaction like fizzing happens. This is a common way to test the pH of soils when special equipment is not available. How do acids and bases burn skin? Positively charged acids break the form of proteins by interacting with negatively charged amino acid side chains. This causes something called coagulative necrosis, denaturing proteins that make up cells but blocking further damage with a layer of dead skin. Bases not only denature proteins by reacting with positively charged amino acid side chains, but also liquefy or saponify fat. This is called liquefaction necrosis and has the potential to be more harmful because it can't be blocked by dead skin as easily. What is acid rain and why is it bad? Industry emits harmful compounds like sulfur dioxide and nitrogen oxides into the air. When these react with water, they can become sulfuric and nitric acid, and when this water is blown around by air currents, you get rain that has a pH of between 4.2 to 4.4, or acid rain. pH is really important for soil and plant health. Certain nutrients are only available at a narrow pH range, and if the soil is outside this range, they will be locked into a form plants can't get. If a soil gets too acidic, nutrient availability will decrease, and the only things available for uptake by roots will be toxic ions like aluminum. Likewise, if the soil gets too basic, plants might suffer micronutrient and especially iron unavailability. Plants have different soil pH preferences. Blueberries prefer acidic soils with a pH of 3.8 to 5.5, while lavender loves a slightly basic soil of 7.3. Different geographical areas have different average soil pH based on complex factors like the parent rock and amount of rainfall. Plant roots can actually pump protons into soil, acidifying it. This acid pumping is part of how plants can eventually weather rocks in the soil. On the topic of ocean acidification, this also poses problems to ocean organisms that make shells, like clams. They build shells out of calcium carbonate, but excess protons in the water will turn the calcium carbonate into bicarbonate instead, making it unavailable for use. But you can at least reassure your students that acid rain won't immediately burn off your skin. What's the strongest acid and strongest base in nature? Hydrochloric acid in your stomach is a good contender, but sulfuric acid found in volcanic gases and nitric acid formed in thunderstorms also have very low pHs. As for the strongest base, calcium hydroxide is found in nature as a mineral known as portlandite. To close, it helps if you can get kids to start thinking about what the pH of drinks and household substances around them are and how that influences their function. For example, they might test the pH of soda to be acidic, and you can talk about how it not only gives a unique flavor, but also helps extend the shelf life. Then you can mention, okay, let's say it's dinner. After drinking soda but before going to bed, what do you need to do? You need to brush your teeth. Toothpaste is basic, which allows it to neutralize the acids from soda in your mouth that might damage the teeth. It's these small connections that'll get students inquisitive. When I first ran an experiment where kids measured the pH of different liquids, they pretty much immediately started mixing them and measuring the pH. They'll see that an acid and a base cancel each other out and bring a mixture to neutral. You can actually challenge them by putting BTB in an acidic or basic liquid and having them try to get the liquid as close to green or neutral pH as possible. And that's all I have for today. As always, you've been listening to Help I'm Teaching. Thanks so much. Leave a 5-star review if you can. It really helps get this podcast out to people who might need it. Sources and transcript, as usual, are in the show notes. See you guys next time.